Welcome back, quadrature fans. My name is Mary and Elena, and it's been a while. Today we will continue with our series. It's a binomial slugfest using polynumbers. Polynumbers, that's an interesting thing. Just a recap of where we're at. Basically, we're doing y equals x to the n. Those are our family of curves. We're not doing anything else, just these curves that look like this. Yeah, it's x squared, x third, etc. And yeah, we're using Weilberger's properties of areas. And these are linearity, additivity, translation, dilation, normalization. Together, linearity, additivity is superposition. Basically, our approach is using what I call box operators. So if we want to know the area of the little wedge, that's wedge over here, it's k sub n times the area of the box. And the slope is c sub n times the diagonal. We are using, in particular, translation of 0 to 1, and then 1 plus alpha. And alpha is a very special number. But yeah, alpha, okay. And so when you translate, that's along the x-axis. On the t-axis, this would be 0 over here, and then alpha. And so the translation of the equation is essentially x equals 1 plus t, because they're translating by 1. When we do our binomial expansion of this translate, and we say t is equal to alpha, basically. So y equals 1 plus alpha to the n, because y equals x to the n. So this requires a binomial expansion, and that is given by 1 plus n alpha plus n minus 1 over 2 factorial alpha squared, n minus 1, n minus 2 over 3 factorial times alpha to the third, and so on and so forth until we get alpha to the n, 1 times alpha to the n. That's our translation equation, okay? And that came right out of here, 1 plus alpha to the n. Okay. And so we're going to be now looking at this. We're going to take this translate equation, and we're going to look at slope and area. And it doesn't matter which one you do first. There's no particular order. But in my scheme of things, I always do both slope and area in one video. It can be busy. There's a lot going. But there are similarities that once you've mastered it for one, the other one looks very similar. Anyways, so we're going to, let's do it. We're going to look at things from the x-axis and from the t-axis. And essentially, okay, let's do the slope. So slope at this point here, at x equals 1 plus alpha, it's the same as at t equals alpha. And so what is that? From the x perspective, this slope here, well, that's c sub n times rise divided by run, this characteristic diagonal, which is 1 plus alpha to the n divided by 1 plus alpha. Well, you can see it's 1 plus alpha to the n minus 1. Okay? That's from the x perspective. That equals Well, you have all of these little functions of t. So let's do it. So you can see the constant always gives you 0 slope. Then you have this linear, that's c1, which we know already is 1 times n alpha divided by alpha. And so you can already see that the slope is n. And you have the others. You have c2 times n minus 1 over 2 factorial times alpha squared divided by alpha, and so on. And okay, so that's your binomial expansion. Looks very messy, but it turns out that you only need just a few of these terms. So we have to expand this part right here. 1 plus alpha to the n minus 1. What is that? When you expand that, that's another binomial expansion. You get 1 plus n minus 1 alpha plus n minus 1, n minus 2 over 2 factorial alpha squared, n minus 1, n minus 2, n minus 3 over 3 factorial alpha to the third, etc., so forth and so on, all the way up to alpha to the n minus 1. Okay, that's the last term that will expand here. And that is equal to this. And then what you have is, you can see there's some cancellation that will occur, namely the c sub n times alpha to the n minus 1. That will cancel out. Well, that's c sub n alpha to the n divided by alpha. That's alpha to the n minus 1. So that cancels out. Similar for the area. If we do the area, we have another box operator. That's k sub n times the rise times the run. So we're doing this from the x perspective. This big wedge right here, that's k sub n. The area is k sub n times 1 plus alpha to the n plus 1. And that equals all of these little areas here. This one is from the x perspective. And then we get the little areas from the t perspective. And those are k0 times 1 times alpha. See, 1 times alpha times k0. K0 is our rectangular. Plus k1, which is the first order, the linear, and that's n alpha times alpha. That forms our box, times k1, which is 1/2. And then k2 times n minus 1 over 2 factorial alpha squared times alpha. And so on, all the way. And yeah, well, that goes all the way to some large number. Okay, we have to expand this portion, this 1 plus alpha to the n plus 1. And that's simply k sub n times 1 plus n plus 1 alpha plus n plus 1 times n over 2 factorial alpha squared, n plus 1 n minus 1 over 3 factorial alpha third, etc., all the way up to alpha to n plus 1. And there will be cancellations. This time there will be 2. One of them will be here, k sub n times 1. k sub n times 1. This will cancel this. And the other one is on the other side. It's this one, k sub n plus to the alpha to the n plus 1. K sub n times alpha to the n plus 1. And all we are left with are alpha terms, alpha square terms, third, fourth, etc. And those have to match the alpha terms here. All right, let's do polynumbers, because this, as you can see, is very messy. So, polynumbers, I think they simplify things. Look at this. Y equals x to the n. Okay. And we've already said that x is 1 plus alpha, so y equals 1 plus alpha to the n. In polynumbers, which I'll simply refer you to Wildberger for polynumbers. I'm assuming that you've seen his videos on polynumbers. But essentially, 1 plus alpha. In another form, it looks like this, kind of this L-shaped thing, 1 and 1. These are alpha levels, okay? Here's alpha to the 0 level. Here's alpha to the 1 level. So it's 1 and 1. And so 1 plus alpha to the n, we would write that as a 1 plus alpha and then to the nth power. And what is that? Well, that's our binomial expansion. Believe it or not, this is it. It's 1 plus n. And there are these alpha levels, alpha 0, alpha 1, alpha 2, but we don't write that down. We want to declutter. Clutter isn't a good thing. So it's assumed that you see them. They are in there. We don't write them down. But we have 1, n minus 1 over 2 factorial, n minus 1, n minus 2 over 3 factorial, n minus 1, n minus 2, n minus 3 over 4 factorial, dot, 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 1. We end at the same one. This is the binomial expansion. And this goes all the way up to the alpha n level. And there could be 50,000 entries in here, but we just say dot, 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 and we're done with it. We don't have to do it 50,000 times. So this is the translation equation, which is this thing here. This and this is the same thing. It's identical. There's no difference here. This is the same. This is a translation equation. The slope, what is slope? Well, it's c sub n times rise divided by run. Here's our characteristics diagonal multiplied by c sub n, and that's slope. That's really c sub n is 1 to the n minus 1, if you think about it. And that equals, if we do the expansion of c sub n times this polynumber 1 to the n minus 1, well, it's 1, n minus 1, n minus 1, n minus 2 over 2 factorial, n minus 1, n minus 2, n minus 3 over 3 factorial, and so on, dot, 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 all the way back to 1, and that's at the alpha to the n minus 1. Okay, so keep this in mind. You can see a similar structure already. If you've done it for here, you can do it for here. That's for the slope. And this is from the x perspective, the big perspective here. Okay, fine. Let's see what the area is. Area is k sub n, and this polynumber 1 times n, 1 plus alpha, right? There's 1 plus alpha, that's what that is, to the n times 1 plus alpha. Okay, that's really n plus 1 power. And so similarly, if we expand that, we get 1, n plus 1, n plus 1, n over 2 factorial, n plus 1, n minus 1 over 3 factorial, and so forth, dot, 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 back to 1 at the alpha to the n plus 1 level. Okay, so look at the way things work. You know, here with the translation equation, we and at alpha to the n, the slope, that will be alpha to the n minus 1, and here alpha to the n plus 1. And this is how it expands. This is from the x perspective. And basically, we now, let's go back to slope. We look at this. This is from the x perspective. And now from the t perspective, well, you know, c sub n, that's our n. Then you have c2, n minus 1 over 2 factorial. And that's our alpha to the alpha to the first level, yeah. And then you have C3, n minus 1, n minus 2 over 3 factorial. And this is at the alpha squared level right here. And so you can see it works its way down. And so, good. Okay. And so let's see what do we got? Well, we know that C1 from here, C sub n times 1 is equal to C1 times n. We know what C1 is, it's 1, right? C1 is 1. So C sub n is equal to n. Okay, we already know this. C sub n equals n. So now we can plug in C1 is equal to 1, C2, what is that? C2 is equal to 2. So we can plug in 2. C3, that'll be 3. C4, that will be 4. C5, that'll be 5. Now look, you got 2 on the top and 2 factorial on the bottom. That cancels out to be 1. 3 on the top and you got 3 factorial on the bottom. That cancels out to be 2 factorial, right? Okay. 4 on the top, 4 factorial on the bottom. Well, that cancels out to be 3 factorial. And similarly, this is 4 factorial and so forth and so on, you know, all the way to C sub n, which we know we cancel. This is a cancellation. So you get 0 over here. So look at this. This is an interesting thing with polynumbers. Basically, we can factor out this n. N is a constant, okay? And we can take it out. Literally, you can take it out, right? You see that? And we can just remove it. And so what we're saying is that C sub n times this polynumber is equal to n times this polynumber. But look at this polynumber. This polynumber is identical to this polynumber. You see the form of it? Literally, what we've done here, we verify that for all 50,000, or how many entries you have here, at this polynumber level, C sub n is equal to n. Not just for this one, but for all of them. This is powerful stuff. I mean, I love it. The whole thing just cancels out. And C sub n is equal to n. And let's look at the area. Area is, well, that's another one. So this is from the x perspective. And this k sub n. So what we're doing is we're doing the area from the x perspective, that's this one, is equal to this area from the x perspective plus this, and this from the t perspective. And we can subtract this area from this big area, and that gives us this area from the t perspective. That's essentially what I've done here. The area, we're looking at it from the x perspective, and this is the big wedge here, minus the area of the little wedge here, okay? That equals these little areas right here. So what is that? Well, first of all, let's do our cancellations. This one is a 0. That cancels out. This one's a 0. Okay. And from the t perspective, well, what we get is, what do we got? K0 times 1 times alpha. So it's K0 here, which we already know as 1. And K1 n times alpha squared. So here's our alpha squared, so K1n. Basically, it's the same thing. We know K0 is 1, right? K0 is 1. And so from here, K sub n times n plus 1 is equal to 1. That's at this level, at the alpha to the 1 level. And so this gives us K sub n equals 1 over n plus 1 from this line here. This is the alpha to the first power. And K sub n times n plus 1 is equal to 1. Therefore, K sub n equals 1 over n plus 1. Well, now that we know what K sub n is, let's plug that into all these other factors and see what happens, right? So we got all of this. Yeah. So this would be 1/2. That's K1. This would be 1/3, 1/4, 1/5. Okay. Now it is 1 over 2 factorial. See that? And then you got 1/3 times, and then here's 2 factorial on the bottom. Well, that becomes 3 factorial. Okay. And this one, and this becomes 4 factorial. This becomes 5 factorial, etc., all the way up to k sub n, which this one actually, k sub n actually canceled out. We got 2 cancellations at the area, but what do we have? What we have is the same form, a polynumber. Here's 0. Let's factor out this n plus 1 because we can bring it out. It's a constant. So k sub n times n plus 1 times n plus 1. If we bring that out, then basically what we end up with is the same form. You got 1 n over 2 factorial, n minus 1 over 3 factorial, etc. Here's 4 factorial. It's the same thing. So you end up with this big polynumber, which is identical. And so what we're saying, we can cancel this out completely, and we get k sub n times n plus 1 equals 1. K sub n equals n plus 1 for the whole thing, for the whole 50,000 entries. And so similar kind of logic as we did for, for the slope. These things tend to crank the same way. They kind of look the same way. A little bit of difference is, here you lose a power, you reduce by 1. Here you gain by 1 power. But otherwise, the mathematic kind of cranks the same way, and the binomial extensions crank the same way. And so we end up with, this is polynumbers. So I'm there in Elena, and before there was calculus, there was quadrature.